Ladies and gentlemen, hello and welcome once again, coming to you not quite live from One Take Studios, where today we have a slew of information. That's right, you heard it here first. We have an official slew of information. Not sure how many things are in a slew. We'll find out. Alright, so today's topic is a broad brush here, is that often we are looking for the number of outcomes that something has for a sample space in order to be able to work with probability. So tree diagrams and counting techniques are topics that are things that help us figure out how many outcomes there are so we can figure out probabilities. So this is like the step into probability for some of these things. Okie dokie. So you are looking in your closet. All you have left in your closet, the only thing that's clean, is a pair of shorts, a pair of jeans, one t-shirt, one sweatshirt, one flannel shirt. Most of us would look at our closet and say, I have nothing to wear. And while maybe there's nothing that you would like to leave the house wearing, that doesn't mean that there is nothing for you to wear. Because quite frankly, we could pair the shorts with the t-shirt, or the shorts with the sweatshirt, or the shorts with the flannel shirt, and that's 3 outfits right there. But we could also pair the jeans with the t-shirt, or the jeans with the sweatshirt, or the jeans with the flannel shirt, and that is 3 more outfits. So we actually have a total of 6 outfits available. Okay. Short of drawing diagrams, this is not quite a tree diagram, I have official one of those coming up here in a moment, how would I be able to figure out that there are 6 outfits available for me to wear? Well, we have something that is called, and there's multiple names for it here. No, there we go. The multiplication rule of counting, or the way that I originally learned it, is the fundamental counting principle. They both refer to the same thing, so you'll probably hear me say the fundamental counting principle. But the idea is this: despite all the big words, we are going to multiply the number of ways each event can occur. In this case, we have 2 events. Event 1, we're going to pick something to wear on the bottom half of the body. And event 2, we're going to pick something to wear on the top half of our body. So the number of ways each can occur, well, there's 2 options here for pants and 3 options for shorts. And the fundamental counting principle says I just multiply those together. 2 options for the first event, 3 options for the second event, multiply them together. Oh, look, that gets 6, which is the same thing I get by drawing diagrams. Alright, so by means of practicing that idea real quickly here, let's pretend that you are putting together your college schedule for the fall, spring, I don't know, pick a semester. And this is what you've got available. You need to take 1 Spanish 3 class, you have to take a college algebra class, and you need a microbiology class. These are the availabilities for offerings, so there's 3 Spanish classes, 4 college algebra, and 2 microbiology on your schedule. How many different outcomes do we have here? How many different arrangements of the schedule can you get? Pause. Take a moment, pause, come back to me when you think you've got the answer. Alright, pause. Did you pause? I hope so, because that wasn't a tragedy right there. We have 3 events, and we're multiplying the way each one can occur. So there's 3 options for the first event, there are 4 options for the second event, and there are 2 options for the third event. Multiply, multiply, multiply. That means that there are 24 grand total ways that you could put this schedule together. Alright, so that is one way of looking at things that is kind of nice. Let's see, I'm going to do this here. What does this look like from the perspective of a tree diagram? Because like I said, this is not an official tree diagram right here. Let's look at a different problem that maybe is a way to suggest how we might mix this idea with some probability perhaps as well. I have a textbook that just... it tickles me pink, because for some reason this book always has urns, and the urns have colored balls in them. Why are there urns with colored balls in them? I have no idea, because all I can picture is a dead clown, which is probably morbid, but there we go. And today they're green and red, so maybe the clown passed around Christmas time, I'm not sure. That's just morbid. Sorry, that's my fault. Anyways, we are going to draw 2 balls out of this urn. And so we can see one set of branches is going to be the first draw, and the second set of branches is going to be the second draw. You have to have a starting point, and that starting point is the very first draw. One thing could happen, another thing could happen. So it is possible on the first draw that we end up with a green ball. It is also possible on the first draw that we end up with a red. So green could happen, red could happen. Let's look at the probability of that for a second, shall we? the probability of, I'm going to use G for green, the probability of green. Well, there are 3 green and there are 5 total balls, and so that would be 3/5. And so I can also use my tree diagram to keep track of my probabilities if I would like. Which means what's going to be over here for red, the probability of, I'm going to use R for red, the probability for drawing a red, well, there are 2 reds out of, again, 5 total. So not only do I have the probabilities here, but on top of that, think about this. What is 3/5 plus 2/5? Grand total, 5/5. This is 1. This is 100% of the things that could happen on my first draw. Logical. Okie dokie. Now, let us pretend that we have drawn a green ball out of the urn. Now what could happen next? Well, on my next draw, I might possibly draw another green. That could happen. Or I might draw a red. Just going to stick on this top branch for a second here with these guys. All right, so green and then green, or green and then red. Okay, that could happen. If I've already drawn a green one and I go to find the probability of drawing a green one again, think about this. One and the other, we're talking, we pulled one out, there's less than there were before. This is dependent, right? You're going to say that? This is dependent? So we are now saying that for the green, there are only 2 remaining green balls left, but also grand total, because we pulled one out, there are only 4 total balls left in the urn. So the probability of pulling a green this time is actually 2 out of 4, or 1/2 if you prefer. Well, what does that mean for red? The probability for red. All right, well, let's see. If we pulled a green the first time, there are still 2 reds available, but again, there are only 4 balls left in the urn. There we go. Okay, I'm going to come back to those numbers. We're going to fill out the bottom part of this. Let us say that on the first draw we pulled a red. All right, so second set of branches. Again, this is our second draw, and we are drawing 2. So we pulled a red the first time. Okay, great. What could happen this time? Maybe we pull a green. Maybe we pull a red. Options, options, options. So if we pulled a red the first time, what does that mean for the probability of pulling a green ball this time? Well, all right, so probability of green. If we pulled a red the first time, there's only going to be, well, there's still going to be 3 green ones in there out of 4, so this is 3 out of 4. 3 out of 4. Can you read that? 3 out of 4? That's not bad. Okay, so 3 out of 4. Okie dokie. Oh, you know what? You know what? Humor me a second. Sorry, this is One Take Studios. Live with it. I want to change my writing on this, because I want to make sure that we are using one of our other notations that perhaps we have learned, and if not, I'm going to introduce it to you real quick. This is an erasable pen. Usually it works pretty well. That's not too bad. Alright, so this is the probability of what? This is the probability of green, given that what happened? Given I pulled a green the first time. This is conditional probability. This is the probability that I pull a second green based on the fact that I pulled a green the first time. And so this one is the probability that I pulled a red based on the fact that I pulled a green the first time. So the probability of red given green. Oh, I like this much better. All right, fixing our notation. Which means for the other one, we are saying for this, that's not bad, we'll fill in the line, okie dokie. So this is the probability of, well, we're looking for the probability of green, but again, this time we are saying that the first pull gave us a red. So the probability of green given red. The probability of green given red is 3/4. And now finishing this up, the probability of, well, what would this be? Red, given the fact that we already pulled a red. So the probability of red given red will be what? Okay, thinking. There were 5. I pulled 1 red in theory. There's 1 red, 1 left out of 4. This is going to be 1/4. Great. Well, what does this allow me to actually do? Well, check out the very bottom of this here. I'm going to slide this up a bit. All right, so not only do I have my diagram of all my possibilities, but I can actually track my probabilities this way as well. So the probability of green, then another green, well, so if this is, if this is dependent, the first probability was 3/5, and then we're going with another green, and that was 2/4. And so I'm looking for the probability of green, then another green. I can do this. That is going to give me something total of reducing 3/10. So I have a 3 in 10 chance of, on my 2 draws, pulling a green and then another green. What about green and then red? Well, that would be green and then red. So we are talking the 3/5 again for the green. But if we go with the red in the second time, wait a minute, that's still the same thing. Can that happen? Yeah, absolutely that can happen. What about red and then green? Well, red and then green, that would be 2/5. I'm going to start writing my fractions slanty here to make a little bit more space. So 2/5 and then times 3/4. What is that going to get me? 2/5 and 3/4. Oh, the same thing. Well, this is really weird. Is this trend going to continue? How about red and then red? Well, there are fewer reds, so getting double red is probably going to be slightly less. So we're talking 2/5 and then 1/4. 2/5 and then 1/4. So what is that going to be? That is 1/10. Wait a minute. This actually makes sense again. This is everything that could possibly happen on 2 draws. 3/10 plus 3/10 plus 3/10 plus 1/10 is 10/10. This is 100% of my outcomes. This is logical. So these add to 100%, 1, because this is everything that could happen. And these also make it so that grand total, we have accounted for all possibilities. All right, so let's move away from that and move into something else that is, can I even say similar? I don't know that I want to say similar. But still in the same vein of things, which means we are still talking about being able to determine the number of outcomes. Focus, focus, there we go. So other thoughts about determining the number of outcomes. Again, we talk about probability being favorable over total. If we don't know how many outcomes there are, this becomes difficult. And so today's topics are all about figuring out the number of possible outcomes. So next up is ordered arrangements, dun dun dun, otherwise known as permutations. So we're talking about having groups of things where the order makes a difference, the order matters. All right, so if I talk about how many ways can you arrange 3 objects? Okay, how many ways can we arrange 3 objects? I would like you to actually pull into your brain from a moment ago. We're going to use part of this idea, this fundamental counting principle, scooch, right there. Multiplying the number of ways each event can occur. Because the fundamental counting principle has a definite permutation slant to it here. If I have 3 objects, I think of this sort of like fill in the blank. I have 3 spots, 1, 2, 3. How many of these objects can I put in the first spot? 3. So the first event, the first spot, is 3 different ways that can occur. Now I have used up one of my objects. So now when I go to fill the second spot in my arrangement, I only have 2 options left to me. And then when I go to fill the third spot in my arrangement, I only have 1 option left for me. So I've got 3 objects. I can use any 3 in the first spot, only 2 left here, only 1 left to use. Multiply the number of ways each event can occur, grand total. There are 6 ways, 6 permutations for this particular set of objects. Did you catch the exclamation part right there? It's a little bit of actually like foreboding for the future here. Ladies and gentlemen, what do you call it when you do 3 times 2 times 1? Do you know that? The shortcut way to write that in statistics and math is 3 factorial. And it truly looks like an exclamation point. 3 factorial. All that indicates is I'm going to start with the 3 and do 3 times 2 times 1. And so factorials, kind of making use of this fundamental counting principle, are one way to figure out the number of permutations you might have for objects. Okay, what if I change the question? What if I have the same song but a different dance here? I'm still looking to arrange 3 objects, but this time I actually have 10 to choose from. How will this change? Well, I got 3 spots to fill. 1, 2, 3. But since I have 10 things to choose from, I could put any 10 in the first spot. So the first location here, that first event, can occur 10 different ways. But the next one can only occur 9 ways because we've used up one of the objects. And this one is going to be 8. This is definitely not going to be 6. Multiplying the number of ways each event can occur, this is not 10 factorial. Because if it was 10 factorial, we would go 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. We're stopping. This is going to be 720. So there are 720 arrangements, different ways to put these things in order if I'm using 3 objects out of a set of 10. This was me using all objects. This is me using some of the objects. If you're using all of the objects, you want to use factorial. All right? So if you have all the objects in play, you have a set of 20 and you're using all 20. Factorial. You have a set of 5, you're using all 5. Factorial. Okay? Or, dun dun dun, and this, I get that this looks kind of scary, but this is actually what just happened right here. If I'm using some of the objects, but not all of them. All right, so please again, notice the classifications. Everything that we are showing so far is ordered arrangements. Everything is a permutation. Order matters. This is using all of my objects. What if I only need some of them? Well, I start with all of them, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and I remove the ones I essentially don't need, which would be from 10 minus 3, which is 7. I'm removing from 7 on down from my permutation list here. This is the fancy way of writing this. The way that my brain works, I usually lean this direction. Can you use this? Absolutely. It's definitely the same thing. We often refer to this as NPR. NPR. P for permutation. And N and R, did you figure this out? N is the number of objects that we have, so this would be 10. And then R is the number that you're using. It's like the subset, so it's the smaller number. So I'm using 3 objects out of my 10. So this would be 10, this would be 3. Calculator. Let's switch over screens for a second here, shall we? Let's jump here and here. Ladies and gentlemen, where is everything fun and exciting? Yup, in the menu, where we have a probability menu. There's factorial. That's exciting. You can tell by the exclamation point. And, ooh, permutations. That's the NPR thing that we just talked about. If you're going to use the calculator for this, you have to tell it what N and R are going to be. And so you have to fill in what are called the arguments. So you need to tell it that N is 10, comma, and out of those 10 objects, you would like to use 3 of them. So you need to tell the calculator what N and R are going to be, and then it'll actually run that entire formula for you. Notice the answer is still 720. So if we jump back to our other screen, the calculator just did this because we asked it to run a permutation. And we said that there are 10 objects with 3, 720. Okay, so you could crank this by hand. You could think about it in terms of fundamental accounting principle, or you can ask the calculator to help you out. And all of these things are possible. All right, by way of contrast, what if the order doesn't matter? Dun, 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 dun! Ladies and gentlemen, if the order doesn't matter, it is a combination. Combination, order does not matter. Permutation, order does matter. How on earth will you keep this straight in your brain? Can I point out one of the flaws of society? Because I think it might help. If you've ever been to school and had a locker, what do you call the thing that you spin on the locker? You are using the lock on your locker. You're using a combination. You're using a locker combination. Does that mean that you can use the combination numbers in whatever order your heart desires and your locker will magically open? Nope, it does not. So ladies and gentlemen, we use the word combination wrong in society regularly. You do not have a locker combination. You have a locker permutation. And this is the movement that I'm trying to start, so I would appreciate your help here, all right? We are going to start calling them by their rightful name. We're going to start calling them locker permutations because the order of the numbers matters. You're going to help me with that, right? No more locker combinations in the world, just permutations. All right, we'll see if that catches on. Okie dokie. So, wait a minute, that question is similar. I bet that's on purpose. So how many ways can you group 3 objects? Notice this was arrange, implying some sort of order. This is just group. So if I have 3 objects, how can I place the 3 objects in a group? How many different groups can I make? And yes, this is a trick question. But most of you won't see it that way, sadly. If I have 3 things, and I'm using all 3 things, and the order of the three things doesn't matter, how many different groups can I make? The answer to that is always going to be 1. Arrangements, permutations, are much more interesting. If you're using all of the objects, we use factorial and we get a whole bunch of different ways that things could happen. If we are using all of the objects in combinations, that means you can only make one group, period, because moving them around doesn't change anything. They're still in a group. So this will always be 1. Consequently, we don't spend much time calculating that because it's 1. Now, this makes life a little bit more interesting. How many groups of 3 objects can you make if you have 10 objects? So again, the difference, the side-by-side comparison of last time, we're talking we have 10, we are only using 3, but we're talking groups, and there's nothing here to indicate that the order of the elements makes a difference. So that means I've got, tell you what, I got more pens. Let me show you something colorful. This, and this maybe, and this. Here we go. So for the moment, I have 4 pens, and I want groups of 3. Well, that's a group of 3. What if I switch the order? That's still the exact same group of 3. Wait, what if I move this one here? That's still the same group of 3. How am I going to get a different group of 3? By swapping one of the items out with something else. Now that is a different group of 3. And so that's what we are talking about right now with this particular example. We're saying I got 10 different things, and the only way to create different groups is to swap out items within the groups. Changing the order is not going to make a difference. This also has an oh so delightful formula that is a little bit scarier than the last one, in my opinion, just because I can make total sense out of this one, and I'm still working on why this one works. You should always ask why things work, and sometimes it takes me a while to figure it out, so I haven't figured this one out yet. Someday when I'm bored, which is, gonna be a while. But notice some extreme similarities here. This has C for combination. The last one had P for permutation. It still has N and R, so it's saying this is the total number of everything that I have, so that's 10 objects, and I'd like to use 3 of them. But this time, order doesn't matter, so these are not identical. Please notice, they still both start with N factorial on top, but this denominator says R factorial times N minus R factorial. All right, so let's bump back over to calculator land, shall we? That's going to put us here. There we go. Okie dokie. So, look at the comparison. Predict for a moment for me, will you? What do you think? If we've got a combination instead of a permutation, but we're still using 10 objects in groups of 3, will we have more or less than 720? Predict. Think of something. What are you thinking? Probability. Combinations. Oh, look, it's NCR. But again, we need to put in the arguments, which is what these are called. So we need to tell the calculator there's 10 of these things, and I'd like you to do groups of 3 for me. But the order doesn't matter. More or less? Ooh, strikingly less. Why? Because rearranging things would give us a lot more possibilities. But since we can't rearrange things to change it, just change out objects, this is only 120. So if you've got identical circumstances, you will always have fewer combinations than you do permutations for this. And so that is going to be 120. All right, jumping back to this guy one more time here. There we go. Okie dokie. So, the calculator just ran this. If you're curious, the calculator said, okay, I'd like to do 10 factorial, because there are 10 objects here, dividing by R factorial, well that's 3 because I've got 3 objects, times N minus R, 7 factorial. And they produced a grand total of 120 different groups. Different groups, not different arrangements. All right, so lots of things to think about today, and individually each one seems like it's probably okay. It's when we start using these in the heart of our probability calculations that life gets interesting. Notice here there's nothing here for probability. This is all the number of outcomes that we are producing, and so that is a different type of thing. Okie dokie, good luck, have fun, and enjoy.